Hello everyone, it's nice to see all of you here. Some of you were on the previous talk, and those of you who were then will probably better understand what I will say. My name is Łukasz, I work at Samsung R&D Institute Poland. Today I would like to share with you an idea we've got in my team. We decided to replace a bootloader on one of our development platforms with Linux kernel and a handful of user-learned tools. This by no means is something new. We did it because others did it before us, and here on FOSDEM I have already seen at least 2 talks about it. But we've got our approach, which I would like to share with you. We think there are several good reasons to do that. One of them us being a little bit lazy, as probably some of you here too, and liking others to help us do our job. We want to avoid double effort that is required to develop to bring up a new platform, because code for both Linux kernel and the bootloader needs to be developed to get a functional platform. And we think there is no need to create code for both and Linux and bootloader. Because the talk is rather short, and I really don't want to miss the ending, I will do my best to tell you everything I've got, and then I will answer your questions. This presentation has got two parts, unlike what's on the screen. The first describes more or less the current state of publicly available bootloaders on ARM Cortex-A CPUs. Angelo said a lot more about that. The second is about our work, how we think it is possible to improve the situation. For those who are unfamiliar with the topic, on ARM there is no standard firmware like BIOS or UEFI on x86. That is why it is a bootloader's job to configure most important hardware components. Let me ask, how many of you have touched a bootloader code or an architecture-dependent Linux code that runs before start kernel function? Just like, okay, we're on the same page. That's nice. In this, maybe some of you are more clever than I am. In this presentation, I assume the booting process comprises the following stages. The firmware is a piece of, this is what others call RBL, Angelo called it RBL. This is a piece of immutable code that comes with a CPU. It cannot be changed by any means. Then there is a bootloader, aka SPL, divided into several stages. And then, of course, there is an OS, the code that implements the application the device was designed for, like desktop environment or multimedia system, or choose yours. An additional task bootloaders sometimes perform is an OS update, especially when the OS is broken. This means a bootloader should be very robust, as it may be the only way to unbrick a device. We concluded that the available bootloaders for ARM have so significant drawbacks, and we need to improve upon that. Following the experience of the Linux boot project, we decided to use Linux as a bootloader. These are the 3 most common bootloaders I could find for ARM. Each of them support different architectures too. There is a lot more proprietary, commercial, custom ones. Until now, in our work, we have used U-boot on most development platforms and some custom bootloaders on products. Every new platform needs a bootloader to be ported to it. You know, you build a PCB, you smash an SoC onto it. To boot it, you need a bootloader. Just to repeat, I mean all the code that is loaded from ROM that runs until Linux kicks in. So that's what I consider a bootloader. Porting a bootloader to a new platform requires writing platform setup code, which will configure the platform to be usable. It turns on DRAM, some clocks, some voltages on board, some basic peripherals like console. Then there is a general purpose code which deals with loading OS kernel from a storage or from a network and starting it. In addition, in traditional bootloaders, the range of options here in this area is somewhat limited. On the other hand, for Linux, there are tons of device drivers, dozens of file systems, and more than one network stack too. And thanks to kexec, Linux can act as a bootloader and start completely new kernel, load it from wherever you want and start it as a new system. This is Odroid XU4. It is based on Exynos 5422 SoC, and it has been a reference platform for Tizen OS for the past couple of years, and almost everyone in our office has one in their drawer. That's why we chose it for this proof of concept. It's well supported in the mainline Linux, and we knew that if it doesn't boot, then it is our fault. We're doing something wrong. It wasn't entirely true, but that's not the point. Now, we fixed like probably 2 bugs somewhere in the compressor code that nobody looks into. It works, and we did something different, and it appeared a fix was needed. There have been a number of similar attempts to push Linux as close to hardware as possible, mostly on x86 platforms, and as I learned today, on RISC-V too. We work with ARM platform, and thus our approach is slightly different. Please do keep in mind also that this was kind of a side project, and we focused on getting the most important functionality available, and we're not bothered by any convenience feature too much. Okay, the boot on Odroid looks as follows. There are 3 blobs provided by the vendor, which is hard kernel, and they are flashed with with appropriate script. They are flashed onto SD or eMMC card, so the board can boot. BL1 does the very basic platform setup, which is turning on DRAM and reads BL2. BL2 loads trust zone and an unsigned U-boot image. Trust zone blob appears to be doing nothing because there are a lot of null bytes, so we don't have source code for it. It doesn't do anything, I think. No, it doesn't behave wrong. We don't have any problems with it. Let's stay with that. All 3 blobs these 3 blobs need to be signed. Hard kernel signs trust zone handler and BL2 upon request on their forum, but this is a little bit cumbersome to change them, so we decided we will replace U-boot, just U-boot. No, we didn't replace any of these. There is, however, as you might see, there is the name of the last node, the BL2, suggests the largest hurdle we faced. That is 1 megabyte limit on the U-boot image. We had to fit within that limit. After a quick recap, we found these 4 tasks were essential to boot the board with Linux kernel as a bootloader. Platform setup. As I said, this was rather quick. The BL1 and BL2 code does all of the setup except for console. We did console with a small, I don't know, 50, 60 bytes shim. That's easy. 1 megabyte is very, very little for a kernel, device tree, and reasonable, whatever that means, userland. After disabling almost everything in kernel, what we could, our Z image took like 950 kilobytes, so we were left with 50 or 60 kilobytes for the userland part. For the record, without such strict limit, we would build a separate bootloading kernel anyway, with different configuration than the one we used for the OS. So 2 kernels are always, we think, required. Maybe not. Maybe the first one could be not that much limited. Linux, luckily kexec worked. However, we had recently some other boards which had some problems with kexec. It appears to be the problem with drivers of some devices that don't shut down devices properly, and when a new kernel starts, drivers try to probe devices. The devices are in states that cannot be handled at the probing stage by the drivers. So this will need investigation. Although we weren't much into providing userland tools, just a few bits to load the kernel started, we found the uroot used in Linux boot, for example, to be a very nice piece of software for that. Much better than, in our opinion, much better than other such toolboxes. Alas, it doesn't support kexec on ARM. We had to use kexec tools, but that's just a minor problem. Thanks to TMPFS, which unlike old-style RAM disk is able to expand in RAM as new data is saved, we could split our init-RAM-FS archive into 2. The first stage comprises only a tiny init we call half-stage init, which mounts FAT partition, unpacks stage 2 archive, or stage 1 full archive, execute /init that is expected to be in the archive, and replaces hsinit. There is no limit for the stage 2 archive, except of course the size of RAM, size and speed of storage, and such things. uroot, short for universal root, is a really nice piece of software I'd like to recommend you if you build bootloading environments. It is a set of basic tools. There is a shell, text editor, ls, cat, and stuff that you find in all the boxes out there. But unlike other boxes, it is written in Go. It can be deployed in 2 modes, source and BusyBox mode. The former is neat because the only binary that is on the initramfs is Go compiler, and every tool that you use is compiled on demand. Unfortunately, it requires much more space and rather strong CPU. On ARM, it was too slow to build the commands. The BusyBox mode is a single binary with multiple symlinks calling multiple functions. At the moment, what we've got, we can configure the kernel to build an image for a selected board. In our case, it is XU4, to boot without U-boot and start another fully fledged kernel. Although XU4 cannot act as a USB device, to use Linux on our boards, we need to develop FunctionFS-based tool to receive files, to receive and download to the flash. We also need to make kexec tool in uroot work on ARM. Why, you may ask? From our perspective, there are following advantages to this approach. Less effort during platform bring-up, because we avoid code duplication. This extends also to maintenance. You don't end up with, I don't know, for example, PMIC driver into repositories in Linux kernel where you need it for power management, and in bootloader where you need it to bring up the platform. Linux, more flexibility. Linux, both the kernel and the userland, is much more capable and flexible than bootloaders available. Two areas we consider crucial are network support and security. Although it is possible to boot over a network today, only TFTP is available for file transfer, which is perfectly fine from a client perspective. However, without an authentication, it is not a protocol I would deploy outside any local network. Support for crypto libraries is very new and quite limited as far as I can tell. And finally, from our experience, the general purpose code like file systems, like network stack, like I don't know, USB stack, not the driver for the hardware, but the rest of the stack, is somewhat in better shape in the Linux kernel and is maintained more regular. That is our experience. In summary, the key features of our approach of what we did, we are definitely ARM-centric because that's the platform we work with. We assume, however, that it applies directly to other platforms which don't employ standards-based firmware, like BIOS or UEFI. Our motivation to push Linux as close to the hardware as possible is a little different than on x86. We're not concerned much about security, like management engine on 86 that affect platforms user, but rather we want to help vendors, ourselves included, to minimize the effort to prepare, to bring up the platform, to avoid the unnecessary effort to prepare two versions of device drivers and keep file systems up to date and so on and so on. Our goal is to find a place and means in the Linux kernel source tree to keep platform board-dependent code which can do platform setup before the kernel starts, and can be built together with the kernel to form a single binary that the firmware, the ROM bootloader can load, alternatively signed SPL. Although this might look like we try to resurrect port files, we don't. The platform specific code that we need is not the same as the board files that were used before device tree became popular. The code needs to bring up only several components, which are not accessed, which are not controlled later on. With this in place, porting Linux would require less effort, less amount of work, and you get really, really powerful boot environment. These are the guys that helped me a lot by either providing knowledge or allowing me to work on this as a side project. And special thanks go to Mateusz, who wrote the small init, the HS init, and squeezed it really hard to fit in the limit. Okay, I managed somehow. Are there any questions?
I'll take the mic.
Any questions?
I guess it's more, it's loud. I guess it's more a comment than a question, but I guess the question comes along. First off, I think it's an amazing idea to use Linux as your driver toolkit, because then you only write your drivers once, right? Doing those in U-boot and in Linux at the same time is a terrible idea either way, simply because you always get this typical fork effect where you have diverging drivers for, like, sooner or later. The big issue I see is how do I put this? The platform init code is something that the ARM world was really proud of to finally get rid of. I don't see us reinventing that or reintroducing it in a 64-bit ARM world. It just is not going to happen. We need to find a different way to get this tiny platform init code in between basically your BL2 and the actual Linux kernel. And this is why I really would like to brainstorm with you on cool ideas we can do. I think we have a couple of things on the plate of what is possible to create a tiny shim that runs before Linux, so that you don't have to put platform code into the Linux kernel itself and the tree itself.
I'm very sorry, but there was something could you come and quick repeat me the question without the mic?
Without the mic. The platform init code you're putting into Linux kernel, right?
Before the Linux kernel.
So is it actually separate standalone code?
It's a single file.
But it's in Linux?
In the source tree.
Yes. I think we need to work on untangling this.
Okay, the question was, is the shim we prepend to Linux kernel inside the kernel tree? Yes, we want to be it inside the kernel tree, and I haven't mentioned that. I have posted RFC patches to the lists, and they are available for commenting. So it's not like we want to push something. We want to discuss it because Linux kernel, the source tree, can become a single stop shop for vendors, for people to boot, code that boots. We're definitely open for discussion.
Also, you can walk with their foot, not with their mouth. So please, if you are going out of the room, please keep somehow silent to let the speaker finish the talk. Thank you.
Okay, it appears I finished.
I think we timed up.
Yeah.
Thank you very much.
Thank you.
So I thank you too.